The universe is perfect, maybe too perfect. Over 6 million years of evolution, we have developed 10 fingers, which then led to the creation of the base 10 system. Coincidentally, or maybe not, every calculation that we have done from this lines up perfectly with how nature behaves. We can somehow explain why we have certain genetic traits. Gregor Mendel's laws of inheritance show us how traits follow these predictable patterns due to the way dominant and recessive alleles are passed down through generations, resulting in ratios like 3:1 for single traits and 9:3 to 3:1 for two traits. Or how the Fibonacci sequence, which is a series where each number is the sum of the two preceding ones, is seen throughout nature. The number of spirals in an acorn is a Fibonacci number. Similarly, many flowers have petals that have Fibonacci numbers. Lilies with 3 petals, buttercups with 5, daisies with 34 or 55, and sunflowers with 21 or 34. Furthermore, as the Fibonacci sequence progresses, the ratio between consecutive numbers approaches the golden ratio, 1.618. This ratio is seen all throughout nature. The ratio of the forearm to the hand. The seeds in the head of a sunflower are arranged in spirals that follow this ratio. Each chamber of a nautilus shell is larger than the previous one by a factor of the golden ratio. The arrangement of branches on trees and leaves, the spiraling arms of hurricanes, and many spiral galaxies, like the Milky Way. The angle of these spirals is also consistent with the golden ratio. But that's not all. The Richard Feynman number 1/137, which characterizes the strength of the electromagnetic interaction between elementary charged particles like electrons and protons, is considered one of the greatest mysteries in physics because no one knows exactly why it has the value that it does. Or what about Nick Bostrom's simulation argument? Natural phenomena exhibit patterns that might be too similar to be coincidences. And this all stems from our two hands. When civilization first emerged, humans did not have a number system, yet the concept of it must have always existed to facilitate trade. For example, the ancient Sumerians used clay tokens to represent quantities of livestock or grain for trade and inventory purposes. Later, these tokens evolved into cuneiform symbols on clay tablets, which represented numbers and quantities. While tokens and stones may have been early tools for counting, it is our hands that ultimately defined our decimal number system. We interpret values in base 10 largely because humans have 10 fingers. But the interesting thing is that even if we use a different number system, the inherent values of numbers remain the same. For example, 100 in base 2. 64 in base 8, and 40 in base 16 all represent the number 4 in base 10. This essentially means that numbers themselves are natural, and thus are a reflection of nature. So this means that numbers might be just an abstraction in our heads. Or are they objective facts about the world? Numbers and mathematical constants appear to be deeply woven into the fabric of nature itself. For instance, pi, one of the most well-known mathematical constants, appears in the geometry of circles and spheres, wave equations, the structure of rivers, and even in the distribution of galaxies. Similarly, Euler's number, approximately 2.718, which explains the exponential growth and decay processes, appears in the distribution of prime numbers and describes natural growth patterns in biology, including population growth and radioactive decay. And as said before, the golden ratio appears in the arrangement of leaves, flowers, and pine cones, creating spiral patterns that follow the Fibonacci sequence. These patterns, known as phyllotaxis, allows plants to capture as much light as possible while minimizing shading. This efficiency can also be seen in fractal patterns. For example, each branch of a tree looks like a smaller version of the entire tree, and each vein in a leaf resembles the entire network of veins. These fractal patterns often represent efficient solutions to physical and biological constraints, such as minimizing resistance to fluid flow or maximizing surface area for nutrient absorption. These are also seen throughout mountain ranges and lightning patterns. But what really makes us stop and wonder if the universe is too perfect is its abnormal amount of symmetry. For instance, snowflakes exhibit hexagonal symmetry due to the crystalline structure of ice, where water molecules bond at molecular levels to form six-pointed structures. Similarly, starfish and sea anemones display radial symmetry, with identical arms allowing them to interact with their environment from all directions. Creatures like butterflies, birds, and humans have near mirror-like symmetry, which allows for sensory organs and movement to be efficient in exploration and hunting. Even at the microscopic level, viruses often exhibit icosahedral symmetry, a highly ordered arrangement that maximizes genetic material within their protein shells. Beyond living organisms, spiral galaxies like the Milky Way follow a symmetrical pattern with arms spiraling outwards in a logarithmic fashion. And this is all due to the symmetrical physical laws of the universe, from the conservation of energy and momentum to Newton's laws of motion. Yet, symmetry alone does not fully explain the remarkable patterns we see in nature. Many of these patterns are formed through self-organization, where complex systems spontaneously form intricate structures. Self-organization results in patterns such as the spots on animal coats, the stripes in sand dunes, and the movements of starling murmurations. The distinctive stripes of zebras and the spots of leopards are classic examples of self-organizing patterns. These patterns are thought to result from a reaction-diffusion mechanism first proposed by Alan Turing in the 1950s. The interaction between two chemicals, one that activates pigment production and another that inhibits it, creates stable patterns over time. Genetic and environmental factors influence the expression of these patterns, leading to unique coat patterns in individuals of the same species. Similarly, sand dunes form linear and star-shaped patterns in deserts due to the interaction between wind direction and the movement of sand particles. Linear dunes, such as those in the Namib Desert, are formed by strong, consistent winds that shape the sand into parallel ridges, and star dunes occur when winds blow from multiple directions, creating intricate star-like patterns. Another example is the Rayleigh-Benard convection. When a fluid layer is heated from below, it can form a pattern of convection cells known as the Benard cells. These cells often arrange themselves in hexagonal patterns. Similar patterns can be seen in certain cloud formations where warm air rises and cooler air sinks in a self-organized manner. Self-organization is also evident in social insects like termites and ants. Termites build complex mounds with intricate ventilation systems, while ants create large colonies with defined chambers and tunnels. These structures are formed from simple rules followed by individual insects. Similarly, starling murmurations, where thousands of birds move in sync, are caused by simple rules followed by each bird. These simple rules are the result of an extraordinary precision in nature. For instance, the gravitational constant is set just right to allow stars to burn long enough for life to evolve. A slightly stronger gravitational force would cause stars to burn too quickly, while a weaker force might prevent stars from igniting at all. If the electromagnetic force, which governs interactions between charged particles, were stronger, atoms would not form stable bonds, and if it were weaker, electrons would not remain bound to nuclei. Similarly, if the strong nuclear force, which is responsible for holding protons and neutrons together in the atomic nucleus, were slightly weaker, protons and neutrons would not bind, leading to a universe without elements heavier than hydrogen. And if the weak nuclear force, which governs radioactive decay and plays a vital role in stellar processes like the fusion of hydrogen into helium, has any deviation, the production of essential elements like carbon and oxygen would be disrupted. Additionally, the cosmological constant, representing the energy density of empty space, drives the acceleration of the universe's expansion. A slightly larger cosmological constant would cause the universe to expand too rapidly for galaxies and stars to form, while a smaller value would result in gravitational collapse. One of the most interesting aspects of this is the fine structure constant, also known as the Richard Feynman number, 1/137. It determines the strength of electromagnetic interactions between charged particles. Richard Feynman called it one of the greatest mysteries of physics because its precise value cannot be explained by any known theory. This constant governs how charged particles like electrons and protons interact with each other through electromagnetic forces. If it were slightly different, the behavior of atoms and the chemistry of life would be dramatically altered. For instance, if it were larger, electrons would be more strongly bound to atomic nuclei, resulting in smaller atoms, and would make it impossible for electrons to transfer between atoms, effectively preventing chemical reactions and the formation of complex molecules necessary for life. And if it were smaller, electrons would be more loosely bound to nuclei, resulting in larger atoms and weaker chemical bonds, making it difficult for complex molecules to remain stable. These constants are precisely aligned to create the universe we see today. But this just leads to more questions. The improbable precision of these fundamental forces and constants makes us wonder whether the universe is natural or rather a simulation created by an advanced civilization. This concept, known as the simulation hypothesis, was popularized by philosopher Nick Bostrom in 2003. According to the simulation hypothesis, our universe could be a computer simulation created by a highly advanced civilization, and our perceived reality is merely a set of programmed rules and constraints. Bostrom proposed three main possibilities. The first is that advanced civilizations do not reach a point where they can create simulations due to self-destruction or other catastrophic events, leading to human extinction before reaching technological maturity. The second possibility is a lack of interest in creating simulations. Even if a civilization reaches technological maturity, it may choose not to create simulated realities. And the third possibility is that we are living in a simulation. If advanced civilizations can and want to create simulated realities, the number of simulated universes would vastly outnumber the real one, making it more likely that we are living in a simulation. However, paradoxically, even through all this symmetry and perfections, there is randomness and disorder all throughout the universe, rooted in the concept of entropy. In physics, entropy is a measure of disorder or randomness within a system, often interpreted as the tendency for systems to move toward a state of greater disorder over time. This concept, known as the second law of thermodynamics, states that in an isolated system, entropy always increases. It explains why hot coffee cools down in a room, or why a sandcastle eventually crumbles on the beach. It also tries to explain the Big Bang. According to the Big Bang theory, the universe began in a highly ordered, low-entropy state and has been increasing in entropy ever since. Stars burn their nuclear fuel, producing heat and light, but eventually die out, leading to the heat death of the universe, a state of maximum entropy where no usable energy remains. The idea of entropy and the eventual heat death of the universe leads to a fascinating concept called the Boltzmann brain. This concept is named after Ludwig Boltzmann, the physicist who pioneered this understanding of entropy. According to Boltzmann's interpretation of entropy, given an infinite amount of time, random fluctuations in a high-entropy system can occasionally produce temporary pockets of low entropy. Over vast timescales, these fluctuations could create organized structures purely by chance. One such fluctuation could theoretically create a fully formed, self-aware brain called a Boltzmann brain with false memories of a life that never happened. This brain would briefly appear in a random, chaotic universe before dissolving back into disorder. While it seems improbable that a random fluctuation would produce a fully functioning brain, the vastness of time in the universe means that such fluctuations should statistically occur. In fact, over the timescales involved, the probability of Boltzmann brains randomly forming is much higher than that of an entire orderly universe forming by chance. This leads to the troubling thought that it's statistically more likely that we are Boltzmann brains with fabricated memories than beings living in a naturally ordered universe. But this paradox is just one aspect of the greater mystery surrounding our universe. Whether we're in a simulation, multiverse, or a natural being, it is fascinating how perfect yet chaotic everything around us truly is. And so, as we continue to ponder the how and why of our existence, perhaps one day the mysteries of the universe will reveal themselves to us.